Okay, let's talk about circuits today. So this is now taking the concept of electric potential and using it to do useful work. So like any other type of potential energy, you can tap it to do work for you, okay? So let's just see what we want to say here. Okay, so let's actually draw our circuit symbols first. I know some of you have taken electronics and you know kind of this symbology already, but let's just review it here, okay? So lines, well, these indicate wires, okay? There's two ways to do resistors. One way is like that, or I think this is kind of the way we'll mostly be doing it, and then, you know, a number in here. So either or you might see for resistors. Don't worry if you don't know what these things are, okay? We'll describe them shortly. Special type of resistor is the bulb. So it looks like a bulb. That one's easy to remember. There's not a whole heck of a lot more that we have to do with this. We might have to talk about some sensors. So for instance, an ammeter looks like this. Oh, oops. Ammeters, you can imagine, measures current. A voltmeter measures volts. Okay. There's also cells and batteries. And the longer one represents the positive side. Okay. Battery just means multiple cells hooked up together in series. And battery here means the same thing it would mean like with artillery, for instance. A whole bunch of, you know, artillery guns side by side is called a battery, and a whole bunch of cells side by side is called a battery as well. Okay. Do you see anything that we're missing, electronics people, that we need to talk about? The other important circuit symbols that we might need to talk about? Ah, good call. Switches, right. So a switch just you know, allows you to complete or disconnect a circuit. Resistors we already did. No, there's no semiconductor stuff. So no LEDs, no simple diodes, no transistors, none of that stuff. That's for later. Okay. This is, what's that? We can mention capacitors, I suppose, but we're not really going to do much math with them. I think they just look like this. One thing we might mess around with is the Leyden jar, which is like an old school version of the capacitor. But as far as using it and doing calculations with capacitors, we don't cover that. But that's what they look like. They're very common in circuits, but just not the kind of circuits we're going to deal with. Okay, so a few rules. A circuit must provide pathway from an area high potential to an area of low potential. And that pathway must be through a conductive element, usually a wire. Or if you're talking about a circuit board, then through the traces on a circuit board, which are a similar concept. They're just strips of metal, really. Okay, so this pathway must be through a conductor. I'm not going to review what a conductor is, because I think we should already know that. Does anyone not know what I mean when I say a conductor? So what sorts of things are conductors in real life? Metals, for sure. Water itself actually isn't. An ionic solution would be, though. So if you were to dissolve salt, say, in water, then it will become conductive. But pure water itself is not a conductor. It does not conduct well. There's also semiconductors, which are things like metalloids, which have various different properties depending on. So let's draw a little circuit here, and let's add a few elements to it that might be interesting. So first things first, we need a source of potential, and we measure potential in volts. So let's go with 6 volts here. And we talked and covered what potential means, like how we measure it, in a previous class. And so we might have in this circuit a resistor. We'll talk about what a resistor is here soon. We might have a bulb, and we might have a switch. Okay. So there's a circuit, and you can see that there's a complete path when this switch is closed from the area of high potential to the area of low potential. The difference between these two plates is 6 volts, or 6 joules per coulomb. So let's just remind ourselves, volts is a measure of electric potential energy. Okay, so volts is equal to the amount of energy we have in every coulomb of charge, and the symbols for that are Q. So energy is measured in joules, and charge is measured in coulombs. What's a coulomb again? Do you guys remember? Yeah, exactly. So it's physically it's a collection or a number or an amount of electrons or protons. And seeing as each one has a charge of one elementary charge, I guess, the coulomb is the collection of those. So a similar concept would be like measuring water in terms of liters, okay, rather than measuring water in terms of individual water molecules. So saying a liter of water, you're actually talking about many, many billions of water molecules. And when you say a coulomb, you're talking about, well, it's much larger than a billion. Does anyone have the number for how many electrons or protons there are in a coulomb? 6.2 times 10 to the 23, does that sound right? I'm not exactly sure if that's right, but I think it's something like that. Or am I thinking of... No, that's the mole. That's the mole. It's not the same as the mole. It might be to the power of 18, actually. Can someone just look it up quick on your... Just get that number for you quick here. 6.2 times 10 to the what? Yeah, 18. Okay. So, little curly e means elementary charges, and they could be positive or they could be negative, right? And 1 volt then has a unit equal to 1 joule per coulomb. Okay, so if you have 1 joule of energy contained in each coulomb, you have a 1 volt potential, okay, which isn't really very high. So there you go. Okay, put that there. Now, when we close the switch here, okay, there's essentially an electric pressure, much like you would find like with water behind a dam. There's a tendency for that water to roll downhill. There's a tendency for current to push its way through your circuit, okay? And as it does so, its energy is expended in creating heat in the resistor, okay, or light in the other kind of resistor, and heat as well, right? Um, so if we were to look at a point in a circuit like this, okay, we were to put a tool called an ammeter on there, what that ammeter would do is it would measure the current flowing through it. So let's talk quickly about current. Yes? Right, right, right. So the question is, does an ammeter affect the circuit? And the answer is yes. An ammeter, even though it's meant to have very, very low resistance, will it has to, like, even the wires themselves, although we consider them to be having no resistance, they have some, and so would an ammeter. Yeah, it would. So it's like that old saying, to test something in science you have to affect it in some way. So to know its true state is very difficult. Generally though, for the types of circuits that we would ever deal with, testing them is not going to affect them really too much. Like, it's not going to matter. But maybe if you were dealing with a very small, like, say something to do with microelectronics inside a computer. Now if you sort of hook a general ammeter up, maybe now you have some issues, but I don't really know. Okay. Anyway, current is a measure of the number coulombs of charge passing a point in circuit. Okay, and in a circuit like this, there's only one path, so the current is going to be the same no matter where you put your ammeter. Okay, no matter where I place it around this circuit, it will read the same value with the switch closed. So units. Okay, so current is equal to coulombs over seconds. Time is measured in seconds. Okay, so 1 ampere, often just called an amp, right, is 1 coulomb passing a point every second. Okay, so there you go. Amps, by the way, is the base SI unit, not volts, not coulombs. I'm not sure why that is, to be honest. I'm sure there's a good reason. I would always think that maybe it would make more sense to have coulombs as the base unit, but it isn't. It's amps. Okay, so that's the base SI unit for electricity. I'm pretty sure they are. Pretty sure they are. Let's talk about power right now while we're on the topic of. Actually, sorry. No, let's not talk about power yet. Let's talk about resistance first. So what's resistance? Anyone give me a quick explanation, simple to understand description of what a resistance is or what a resistor is? It's kind of right in the name, yeah. Exactly. Peds, flow of electrons. Or the flow of charge, let's say, because although we know now that it is electrons flowing, all the formulas basically, and all the way that we're going to talk about electricity is based on positive charge flowing. Okay, and we sort of discussed why that is. It was a mistake made by Ben Franklin back in the day. He thought positive charge was on one item when it was really on the other. You rub them together statically. So impedes the flow of charge. I often like to write it like this. Just to me, it's easier to remember, but I guess this is the proper way to do it. And the way I like to think about it is, so what we're saying here is for a given voltage, for a given potential, you get some flow of charge, and that's sort of regulated by the resistance. So another way I think of explaining this or looking at it is like, let's say we have this here, okay? Now if you increase the voltage, right, you're going to increase the current, okay? And depending on how much resistance there is in your circuit, you're going to get maybe different values here, okay? So just quickly on what we mean. So here's some resistor. Let's say that this is variable, so we can like raise the voltage up, raise it up, raise it up, raise it up, and we can measure current through it. As we increase voltage, we will increase current, okay? Depending on what we have here in terms of resistance, all right, well, that will be represented by the slope of this line. So the slope here is higher, so delta V or delta I. This has a higher resistance, so in other words, for a given voltage, we have a lower current than we would for this guy. Okay, so this is a higher resistance and this is a lower resistance. Does that make sense? How do resistors work? Does anybody know? Right. So I think the easiest way really to think about it is you can almost consider wires to be like pipes. Okay. So if you have a nice fat pipe, okay, there is less stuff, I suppose, in the way of your charge traveling. So remember, in reality, you have, if this is a piece of wire, okay, you sort of have this kind of system where you have these delocalized electrons, and if you apply a push, in other words, if you force electrons in one end, really what's happening is they're reacting to a field, but you can imagine it as pushing electrons in one end, right? They're gonna spread this sort of wave from one to the next because they repel one another, and this charge is gonna push through. So now if we imagine all of a sudden there's a narrow part on the pipe, okay, well that's gonna cause a higher, literally a higher resistance to electrons getting through there, okay? And, for a given push on this end, which we call voltage, you're going to have a lower flow. And like with water in a pipe, right, if you have a low flow in one spot, that affects the entire circuit, right? So if we put a resistor anywhere in a circuit, at least if it's a fully series circuit, if we put a resistor anywhere in there, it's going to slow down the flow of the whole circuit, okay? Does that make sense? Okay, so this is a way to think about it. You can actually make resistors with more narrow wire. That's often the way it's done, like so inside a stove element. There's a really thin piece of wire. It also goes based on materials. Different materials have different resistances. For instance, if you were to say put a block of rubber or something right in the middle of a circuit, well, that would have a very, very high resistance, such that it would basically stop the flow, and we would call that an insulator. So really, with enough push, okay, with enough voltage, with enough energy, even if you were to have something that's generally considered to be a resistor in here, like even I don't know, say like a piece of plastic or something like that, if there's enough voltage, you'll just arc right through that. We saw that with the Van de Graaff. Air is a good resistor, but if you put enough potential, charge will push right through the air. Okay, so with enough voltage, anything becomes not a conductor per se, but charge can be pushed through it, including your skin and your body, and so on. So this would represent basically a resistor. Okay. By the way, just back to what we were talking about there. Here, Ohm's law, and I sort of didn't really finish what we were talking about over here, so I'm just going to rewrite that. This is Ohm's law, and it's measured in volts per amps, and the unit of this is ohms, so 1 ohm is equal to 1 volt per amp. Okay? So let's do so what we really want to get to here is circuit analysis. I'm not really going to formally write out these rules because I think they just sort of make sense as you start to analyze circuits, but the first thing we'll talk about quickly is a series circuit. That is exactly like it sounds. It's where we have one or more resistors in series with one another. So in other words, the current has to travel through more than one resistor. Okay, so if you can imagine, current leaving here, here's the current, okay, encountering first one resistor, then another, okay, from the, it's hard to say this, but I guess from the perspective of that current, right, it's hitting two narrow passageways on its way from plus to minus, right? So from its perspective, it doesn't really care what order it hits them in. It just feels the resistance, and it turns out that in series, the resistances just add together. Okay, so in series, resistances add. Okay, so what I like to do is if you were asked to analyze a circuit like this, like say someone said to you, find current through and voltage drop across each resistor. Okay, you would do it this way. Now we need to know what the voltage is, so let's make it a 10 volt. Okay, so it's a 10 volt circuit. Step one, if you were to analyze this, would be to recognize that these are in series and they add. So therefore, it would be the equivalent circuit just having a 5 ohm resistor in it. Okay. So if we have this in our back pocket, Ohm's law, it's very useful. Okay, if we want to solve, say, current first, what's the current through this circuit? Well, you just rearrange to get I equals V over R. You will have, in this particular circuit, 2 amps flowing. Excuse me. So what that means is, since these guys are in series, the current has to be the same through the entire circuit. So 2 amps flows through there, 2 amps through there. No matter where I put an ammeter on this circuit, it's going to read 2 amps. If I put it here, 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 it doesn't matter. There's 2 amps leaving, and there's 2 amps returning into this cell. Okay, does that make sense? Okay, so now the second thing was, okay, so we found current through. It's the same through both resistors, but what is the voltage drop across them? We know from here to here, the voltage drop has to be 10 volts, right? There's a 10 volt difference between the start and the end of the circuits, or of the loads. By the way, load is another, it's another word for resistor. Okay, so what we can do now is we can go back and we can say, okay, for each of these resistors. Sure. Okay. We can take the 2 ohm resistor up here and we can plug in, well, it's got 2 amps flowing through it, and it's a 2 ohm resistor. So it must have a 4 volt drop across it. And there's 2 things we can do now. We can realize there's a 10 volt total drop and say there's 6 volts across here. Or you can just do the math again for the second resistor. 2 amps through, 3 ohms, and 6 volts. And these need to add together to be your total drop. Okay? So it's a quick, simple circuit analysis of a series circuit, and that's just how those go. Okay? Are we good there? Are there any questions about that? Adam, questions? Yeah. This part? Okay, which part, what is it that you don't understand? Like you mean in the individual resistors? Okay, so basically, right, there's three variables here. There's voltage, there's current, and there's resistance. So the first thing we did was we looked at the entire circuit, the equivalent resistance of the entire circuit. This is called the equivalent resistance. This would be the actual circuit, right? So if you imagine, we look at this circuit diagram, you've got a 2 ohm, say, light bulb plugged in, and you've got a 3 ohm light bulb plugged in series on the bottom branch there. Okay, you with me? When I turn on my potential, when I flick the switch, right, and allow charge to start flowing, the circuit experiences these as adding up to 5 ohms total. Okay, so 5 ohms total. If we know potential, we know resistance, well, I equals V over R. We have 10 volts total divided by 5 ohms because this is equivalent to being 5 ohms. You'll have 2 amps flowing in this circuit. Okay, now since it's all in series, we know there's 2 amps here, 2 amps here, and 2 amps here, 2 amps here, 2 amps wherever we look. It's continuously flowing, no matter where we look. It's like a train going around, right? The train goes the same speed, so the same number of train cars pass every position, no matter where I look, like trains in a circle, right? Are you with me? So then what I'm saying is, now let's look at an individual resistor. Well, here's the resistance, it's 2 ohms, there's 2 amps flowing through it. So V equals I times R. I is 2, R is 2. 4 of my potential 10 joules per coulomb get dropped off at this resistor if you want. Okay? The other 6 get dropped off over here. If I only had one resistor here, what would be the voltage drop across this if this one were suddenly removed and there was just a wire through it? This would all of a sudden absorb or dissipate the entire 10 volts. Okay? Does that make sense? Dissipation. So what is a resistor actually doing? It's not removing electrons. It's not doing that. It can't do that. It's not doing that either. Remember, right? If I weigh a circuit, it weighs the same before and after, regardless of whether there's stuff flowing through it, right? No matter is leaving, but something is happening. Something is happening as charge passes through a resistor. What do you think it's doing? How? Heat, right? It's just a way of converting potential energy into heat. Now, would I ever make a circuit that just has 2 resistors on it, like this? Maybe. I just want a heating element, right? I just want to make heat. So I pass current through, I put a resistor in the way, the resistor gets hot, and I might use that heat. Generally, however, resistors are used to control voltages in circuits and to control current in circuits, right? So, for instance, something that we did the other day in our club there was we wanted to run LED lights. But LED lights can only accept a certain amount of voltage. So what do? You put another resistor in front to take up some of the voltage drop so that your little light doesn't get over voltage and doesn't burn itself out. So that might be one use for a resistor. I mean, there's tons of them, but that might be one where you want to drop voltage so that, if you have a 10 volt circuit here and, this can only take 6 volts, for instance, well, you put a 2 ohm in front and boom, all of a sudden you have the right voltage drop across it. Does that make sense? That's why you would use just a general resistor. What resistors really represent, or loads represent, would be like some useful items. So let's say this is a circuit in your house. We generally don't wire houses in series, but let's just say we did. This might be like something useful. Yeah, totally. This might be something useful in your house, right? We use the general term resistor, but it's better to think of it as a load. It could be an ironing, it could be an iron, it could be a coffee maker, whatever, right? Every tool in your house that uses electricity has some resistance, right? And it uses energy to do a useful task. So we just draw it generally like this to give ourselves an easy way of looking at a circuit and not have to say, this is your kettle, this is your flashlight, this is your whatever. It's just a general way of talking about circuit. It might not just be heat. It might be, like we say, it might be a an electric motor or an LED light or a normal light or a fluorescent light or a computer or whatever. Yeah. Right now, only DC. Yep. 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 With um um well, AC is different, right? So with AC, essentially what's happening is what you have is you have an it's alternating current, but what you have is basically, if you can imagine taking this battery and flipping it over, right? Flipping it over 60 times a second or at 60 hertz. So what would happen is you get an oscillating current back and forth inside your resistor, right? So for stuff in our houses, they're made to run on that. So if this is a light bulb, it does not matter to the light bulb which way current is flowing through it, right? It's just the electrons aren't moving very far. They're just jiggling back and forth, and they're, emitting energy as light. So that's that. In terms of what we're going to talk about, it doesn't really matter whether you're talking about AC or DC. They'll behave essentially the same. It's something like this with the big robust resistor. But if you're talking about the inside of computers or you're talking about sensitive electronics, then it does matter. Lots of electronics can't run on AC. Semiconductors, for instance, only tend to work one way. So things like diodes will only allow current to travel in one direction. And then you have sort of other issues to think about. But, in terms of our day-to-day lives, it's sort of irrelevant a little bit as to whether it's AC or DC. You're not going to really notice a difference. You flick the switch, the light turns on. Whether that's DC or AC, for something like a light bulb, it doesn't matter, right? We will analyze DC circuits, though. We won't really analyze AC circuits. Although, it's pretty much the same for a general day-to-day circuit. It doesn't really matter, okay? So we would have, if you want to talk about, AC, I guess you could consider it to be null in the middle, +5 and -5 for a total of 10 volts difference between the two. But let's not complicate it at this point, okay? Parallel circuits. So parallel. So parallel circuit helps me a lot to think about it in this way. So the first thing I like to do, just to help myself get through my mind what's going on here, is to start with a parallel plate system. Now we talked about what the fields look like inside of this. And we did generally talk about this, but we didn't actually put it in notes. Now imagine, right, again, let's put whatever, 6 volts here. What we're saying is there's a 6 volt difference. So in other words, there's 6 joules per coulomb in charge that's here, okay, and it will lose that amount as it travels to the negative plate, right? So if we give a path here, okay, we know there's 6 volts across this situation, right? And if we put another one in here, another resistor, 2 ohms, we also know there's 6 volts across that. In fact, as we keep adding and adding and adding more pathways here, all of them will have an entire 6 volts across them, right? Because it's the potential difference between the two plates. We're adding different pathways. So no matter what I put in here, I could have an insanely high resistor, really low resistor, whatever. It doesn't matter, and I could put multiple ones in here, and each one will get the full 6 volts across it, okay? As I add more resistors, you can think of it as adding more pipes, right? And what that does is it causes more current to flow, right? The more resistors I add, the more current I'm going to flow. Our example, I think, that I showed or talked about the other day was, imagine a water balloon, and I poke one hole in, well, it's going to have water flow out of it. If I poke another, more and more and more, right? This is the same concept. It's like we're poking holes in a water balloon by adding more resistors. Sometimes people have a problem with this, that adding resistors decreases the overall resistance, okay? So resistance in parallel circuits has a little bit of a different way of working it out, okay? Adding resistors in parallel decreases net resistance. It seems counterintuitive. We're adding resistors, yet we're decreasing resistance. So there's a little rule. Ooh, there's a straight line drawer here. Do you guys remember, does anyone remember what the formula is for parallel resistors? Do you remember, Lyle? Okay, so let's draw a generic parallel plate resistor here, or parallel situation. Okay, so just before we move on, or just before we get to that, houses are wired in parallel, and what this means is, like, if this is a light socket, and this is a light socket, and this is a light socket, if these things were in series, the more lights that we added, the more resistance we would have, the less current traveling through, and therefore the dimmer the lights would get. With parallel systems, though, all the lights get the same voltage across them, and therefore they'll run just as if they were the only thing in the circuit. Okay, so this is the way it's done. What has to happen, however, is the amount of current gets higher and higher and higher as we add more and more pathways for it through the circuit. We could really continuously add forever and ever. Of course, at that point, the current becomes so high over here that your wire might get hot enough to start a fire. So there's rules about how many you can put in in-house wiring. But the net resistance of this works like this. Okay, so parallel resistors work like that. So let's do an example. 6 volts. Let's go with 2 ohm. Let's do a 3 ohm and a 4 ohm. Okay, and let's put an ammeter there, ammeter there, ammeter there, and an ammeter there. And let's talk about a voltmeter. Voltmeter measures the voltage between 2 points. No matter where I attach that voltmeter, it will always read 6 volts. However, each of these ammeters will read different amounts. Okay? Each branch has its own current going through it. The total current must be equal to the sum of individual currents. Okay, so the sum of all the individual branch currents must equal the full current. So the way that we're going to deal with this is we're going to draw the equivalent resistance circuit and then work our way backwards, okay? So what we want is 1 over a half plus a third plus a quarter, right? That's 1 over R1, R2, and R3. These are ohms. Let me just grab my, can I do that in my head? I don't think I can. We should get equal to 0.92. Okay? So what we're saying is, if you add up all of these resistances, okay, in parallel, the equivalent of this is 0.92 ohms total. Little pointer here, your equivalent resistance will always be lower than the lowest resistor. Why is that true? Someone help me out on that? Why will this equivalent resistance always be lower than my lowest resistor? How did that happen? Is that just an accident? Did I just accidentally touch it there? What a fluke. So why is that? Why is it that the resistance here I know will always be lower than my lowest resistor? Why is that? Right. So if I only had one resistor here, right, if these were gone, then the resistance would have to be 2 ohms. If I add another one, though, that decreases the resistance, like popping another hole in the balloon. So it has to drop below 2 ohms. Does that make sense? So you get 0.92 at the end of the day. So now what we'll do is we'll go I equals V over R. Let's find out the current. So we've got 6 volts, 0.92 ohms. So we're probably just over about 6.5 amps. So there's 6.5 amps leaving and 6.5 amps coming back. Remember, amps is coulombs per second. Okay? So now what we want to do is we want to figure out the current through each individual resistor. Okay? And it's actually not hard, right? So we know I equals V over R. So for the first resistor, voltage, remember, is the same across all of them. 6 divided by 2. We have 3 amps there. Here we have 6 over 3. We have 2 amps there. So that's 5 amps. So what will we have through the last one, do you think? Without even doing the math. Got to be 1.5, but we can double check that. 6 quarters, yeah, checks out, should be 1.5. Okay? Does that make sense? We got 6 volts across here because they're all in parallel with each other, so therefore they have the same voltage across each. And if we just use Ohm's law, we should be able to figure out current through each one of these. Are we good? Okay, last but not least, we might as well get this all done. Let's do a combined circuit. Okay? So this is also known as the series parallel circuit. Okay. Let's draw a nice little circuit here. So all we got to do now really is we just have to take into account what we've talked about before and put it to work. And this is where these Kirchhoffs rules come in. And they're basically just talking about how you go about analyzing a circuit that looks like this, that has some elements in series and some elements in parallel. Okay? I'll put a 12 volt on here just for fun. Now what we're going to do first is we're going to analyze the different branches of this, and we're going to get this down to its equivalent resistance. Okay? So if we look, there's a section in parallel over here, and there's a section in series. This resistor here is in series with this parallel section. So the first thing we'll do is we'll pare this down to its equivalent resistance. We should have that. And you should get about 1.7 ohms. Okay, so 1.7 ohms. So what I like to do is I like to redraw the circuit. Oops. Sorry about my lack of skills with this thing. Okay, and then now you notice that these two are in series with each other. So as you continue to pare this down to its simplest or its equivalent form, you add them together now that they're in series. All right, so there it is. From a perspective, if you want to talk about it in terms of having a perspective, but from the perspective of this source of voltage here, this source of potential, it feels as if there's one 3.7 ohm resistor on the whole circuit. So we've pared it down to its equivalent resistance. So what's the purpose of that? Well, now what we can do is we can sort out what's the current leaving. Once we know that, we know that that entire current has to pass through here. Then we can figure out the voltage drop here. And then we can figure out what the remaining voltage drop is across each of these. And we can sort out the current and the voltage drop across all the resistors in the circuit. Okay? You're going to use what are called Kirchhoffs rules, whether you realize it or not. Ooh, did I get to the end of my page? Is this as far as I can go? Apparently it is. So we'll have to try to squeeze it all in here. So we know I equals V over R. We've got 12 volts, and we've got a total of about 3.7 ohms. About 3.2 amps. So 3.2 amps. If we look, 3.2 amps has to pass through here. There's no alternative way for it to go. It all has to go through there. Okay? So if V equals IR, let's figure out the voltage drop that happens at this resistor right here. 3.2 amps times 2, 6.4 volts get lost here. All right, so 12 minus 6.4, 5.6 volts drop across each of these. Okay, so something I'll do here, just to make it easier for us to keep track, is let's make a little chart. So we've got a resistance, we've got a voltage, we've got a current, 2, 3, 4 ohm resistors. By the way, the symbol for ohms is an omega. If you can't tell what I'm drawing, it's like a horseshoe thing. Excuse me. All right, so we know the voltage drop here is 6.4 volts, right? We therefore know that it's got to be 5.6 volts here and 5.6 volts here. Because these are in parallel with each other, right? They're in parallel. So the voltage drop here is 6.4. That means of the total 12 joules per coulomb, 6.4 joules per coulomb have been lost. So whatever continues on here, some current goes this way, some current goes this way, right? But at this point, neither of these has lost any potential. Each has 5.6 in it. By the time I get down here and returned, we now have 0 volts, so it's 5.6 voltage drop across each of them. Got it? Correct. The same amount of potential exists. This is like parallel plates with a 5.6 volt connected to it. Okay? Yes. It's not. It's not aware. I suppose it's like feedback. I mean, the way that I think about it is, okay, let's imagine that I'm water in a Manitoba hydro dam, right? And there's a pipe leading into the dam, and there's a sluice gate on there that they can open and close. Okay? Well, the flow through that pipe, no matter where I look in the pipe, before or after the sluice gate, right? The flow of that is regulated by me opening and closing the sluice gate. It could be hundreds and hundreds and hundreds of meters away. Is the water aware that a sluice gate opened? No. It's just the interaction, I guess, of all the particles in that pipe along the way, right? So you think about this. This is like a sluice gate, right? So this is like a water pipe if you want. Here's pressure. If I open this up a little bit, to 2 ohms wide, it doesn't know. It's not like aware. It's not like they're sending feedback, but there's always this push to push electrons through. This 2 ohm only allows so much flow. Remember, this entire thing is filled with matter the whole way along, right? It's not like it's an empty pipe that all of a sudden water starts singing along. It's made of matter, right? There's protons and electrons all the way through this entire thing. So if you want, you can think of it like pipes filled with clay or mud or something like that. If I start pushing here, this is going to start moving here. It doesn't have to be aware. It's just that, that transfer, I suppose, of repulsion, I guess, since we're talking about charge, all the way along and through the thing, right? So it doesn't matter like what kind of networks of pipes I have through the whole thing. If I'm pushing here, certain resistance will be fed back, I guess, through the system, no matter what. So it doesn't have to know. I know it's hard to understand. It doesn't have to know. You have to do an analogy to think of why it would work this way and why it makes sense, you'd have to reanalyze the circuit. Like if you're saying if I put like a 10 ohm in here instead, yeah, there's going to be, that that has lots of effects, right? So there's 10 ohms here. Now all of a sudden we've got an 11.7 ohm circuit. So what does that do to current? Well, it drops the current. If I have a lower current here, right, do I have the same voltage drop? I don't know. You have to reanalyze the circuit, right? Whatever voltage drop we have here, the remainder falls across here, okay? So yeah, it's all about paring it down and working backwards and sorting each thing out individually in the circuit. And it will take practice, and I'll give you practice. Don't worry. Okay, so current through here, just get her done. 3.2 amps go through there. And then the last things we have to do is just figure out what happens at each of these. Okay, so if we want current through, I equals V over R. We have 5.6 volts drop here over our 3 ohm resistor. Oops, my calculator shut off. 5.6 divided by 3. You should have about 1.9 going through this resistor, so about 1.9 amps. And through the other one, just replace that with 4. 1.3. Oh, whoops. Yeah. Sorry, guys. You're right. Not thinking. Sorry. There we go. Is it really? Oh. No. These have different current through them because they're different resistances, right? They have the same voltage, but one's a smaller pipe. But what does have to happen, right, is these two currents have to add up to this total current, right? So total current 3.2 amps comes in, some of it goes down this pipe, some of it goes down this pipe, and then they come back together and 3.2 amps comes back in. So these do not have the same amount of current going through them, and that makes sense. They have the same voltage across them, the same pressure if you want, but different widths of pipe, okay? So there's 3 types of circuit, right? Series and parallel, and then series parallel mixed together. And you can come up with all sorts of different scenarios, and you can use this method to work it out. Much more complicated ones too if you want. Okay, we'll end it there.